So do you remember the formula that I had you kind of memorize for like percent increase and percent decrease?
Yeah.
Okay, so what was the like percent increase formula?
A equals P parentheses 1 plus R.
That's for percent increase, right?
Yes.
All right, and what's the percent decrease formula?
The same, but it's 1 minus R.
Good. And the reason why I had you memorize this formula also is because it applies to these types of problems.
Okay.
Okay, it's similar logic, similar formula. All right, so this is the general formula that'll be used for like exponential decay.
Okay.
The only difference is you'll have like powers up here. Okay, so the nice thing about half-life is you know your percent rate, your percent of decline. Just making a mess right here. Hold on. All right, so let's do the first problem. The cost of producing transistors decreases by, well, this isn't a half-life problem though, but decreases by 20% every year. All right, so if it currently costs $495 to produce a billion transistors, how much will it cost to produce a billion transistors in 6 years? All right, let's start with this one first. So it says how much of a radioactive kind of nitrogen will be left 20 minutes after the half-life is, if the half-life is 10 minutes and you start with 396,240 grams. So, and I think you explained half-life correct. So like, if let's say, so if the half-life is 10 years, how much of this is left in 10 years?
Do you divide it by half the process I was talking about?
Uh-huh.
Okay.
So like in 10 years, it's just half that, right?
Mm-hmm.
And then 10 years after that, it's half that.
Mm-hmm.
You just keep chopping down, right?
Yeah.
Okay. So half-life is a 50% decrease. All right, so we have this formula right here. So how would we put a 50% decrease in this formula?
1 minus 0.5.
So A is equal to P times 1 minus 0.5. All right, so, and how much are we starting, which of these numbers represents what we're starting out off with?
P.
Good. So we have A equals, and what's our starting off amount? 396,240. And then what's 1 minus 0.5?
0.5.
Right, so 396,240 times 0.5. Okay, this number up here, and it gets kind of tricky in the future, so you have to kind of think about it, is how often you're achieving your half-life.
Okay.
Okay, so we know the problem tells us that the half-life is 10 minutes. All right, so that's what the half-life is, but they want us to do it for how many minutes?
20.
20. So how many 10 minutes do we have?
2.
2. So that 0.5 gets applied 2 times because there's 2 half-lives.
Okay.
Okay, that's the confusing part because some people want to put the 20 up there and all this stuff, but you always have to think of like, all right, well, how long is this half-life, and how many of those half-lives are passing by, and that's your power. For the most part, but the way they can make it kind of tricky is like, the half-life is let's say like 2. Let's say that the half-life is something weird like 1 hour, right? And then like over here it's in minutes, and then you have to like kind of think about that.
Okay.
All right, so then we punch that out. All right, so we got PEMDAS, we got your 0.5. Man, there we go. 0.5 to the power of 2 times 396,240, and that answer is 98,060, which is right. Come on now. Oh, that. Okay.
Mm-hmm.
All right, let's try this bacteria one. In the SAT, you can straight up just get like a bacteria problem. So a colony of 3,960 bacteria doubles. Oh, cool. All right, this is doubling. This is not decay. We're increasing.
Okay.
So which formula are we going to use?
The first one, the increase.
Mm-hmm. What's that formula?
A equals P times 1
Uh-huh.
plus R.
Good. So A equals P times 1 plus R. So a colony, all right, so, and double, well, what percentage is double?
0.5.
Well, so doubling, like if, let's say I had, well, here's 0, here is like, I don't know, I guess 100. All right, so what percent is it just to get to 100?
1.
So not 1%, but 1 in decimal form. So like, let's change it to 400. All right, so if you, like, what percent of 400 is 400?
400.
100%. So 400 is 100% of 400.
Yeah.
Does that make sense?
Yes.
All right, so if we're going to go, oh, and if we were to double 400, what would that new number be?
800.
800. So if this is 100%, then what is it? What's the percentage to get to 800?
200.
Yeah, 200%. It's 100%, which is 1 in decimal form, which is that guy, plus another 100, plus another 100%. Okay, so this 100% is this number, and this 100% is this number, but you got to put it in decimal language. 1. So once you do a lot of these, you're going to be like, oh, it's a doubling problem. I'm going to do that.
How do I assume that it's a doubling problem?
Doubles.
Oh, it literally will tell you. Okay.
It'll tell you. And bacteria always doubles. It's like a thing of bacteria. It's going to double. But the problem will also tell you that too. And so you're going to go like, so 1 plus your 100% growth. Your 1 plus 1. All right. So, and we know the starting amount, right? 3,790. 3,790. Okay, and we got our 1 plus 1, which is 2. All right, so it doubles in size every 200 hours. What will the population be? What will the population be 1,000 hours from now? So what would we put for our power up here? $1 million to get this right. I'm going to go write you a check.
2?
No, because you've lost your mind.
I know.
So if you have okay, so this, you can only apply this 100% every 200 hours. But how many 200 hours do we have?
Oh, 5.
Yeah. So your doubling period is every 200 hours, and you have 5 of those doubling periods.
Okay.
So this is the hardest part of the problem.
Okay.
So then you want to put your 5 right there.
Okay.
And that's it. You punch it out, you get your answer.
Okay.
All right. Let's try this over here. So the half-life of radioactive kind of beryllium is 53 days. All right. So they're telling us the half-life. So they're telling us every 53 days we apply that power. All right. And it's a half-life problem, so is there going to be a plus here or a minus here?
Minus.
Minus. All right. And at least I know what number goes here, what number goes there.
So will I be looking at half-life problems and doubling problems? Those are like the 2 variations?
Yes.
Okay.
So
like kind of in comparison to like an increase and decrease in percent, like the same kind of thing?
Correct.
Okay.
And the only difference is you have a power.
Okay.
Okay, so every 53 days, right? How much will be left after 159 days? So how do we figure out the power that goes up high?
How many times is 53 going to 159?
Perfect. That's it. So 159 divided by 53. 3.
Okay.
All right, so what's our power?
3.
Power is 3. And we know it's decay, so it's 1 minus, right?
Mm-hmm.
And it's a half-life problem, so it's 1 minus what?
0.5.
0.5.
So half-life problems are always the equation of A equals P times 1 minus 0.5
Mm-hmm.
exponent.
And I remember it as, like, in percentage, how do you get half of anything? Like, I don't know, if something's $400 and you want to calculate, or $400.23, and you want to calculate half of that, you multiply it by what?
0.5.
0.5. So, and this gets you your 0.5.
Mm-hmm. Okay.
Okay, so that'll get you your half, but then this is how many times you're applying that half.
Mm-hmm.
Okay, so we have our power up there, and we're starting off with this number here. So where do we put that number?
Is that where we're multiplying it by?
Mm-hmm.
Okay.
Because that's what you're starting off with. So that's what you end up with, which is what we're figuring out, and this is what you're starting off with, which is 6,848. So it's 1 minus 0.5,
0.5.
which is 0.5. Take that to the power of 3, multiply it by 6,848.
Okay.
Go ahead. Okay, so this one here, we have a 20% decrease. Well, guess what we're putting there?
The 20%.
Yeah, so now instead of going half every so often, it's just going to go by 20% every so often.
Mm-hmm.
All right, so we're going to have, all right, so A equals P times 1 minus 0.2. All right, and if it currently costs $495, that's what it originally is, and we're doing our 20% decrease. Well, 1 minus 0.2 is what?
0.8.
0.8. How much will it cost to produce a billion transistors in 60 years? I'm sorry, in 6 years. All right, so it's this percentage is applied every year. So this is applied every year.
Mm-hmm.
And how many of those every years do we have in this problem?
6.
6.
To the power of 6. Okay.
That's it. Go ahead, punch it out. Tell me what you get. And that's the answer right there.
Okay.
Any questions?
I think I just need to practice them on my own. Like right now, like I understand what you're doing, but I think I need,
Yeah, so the two important things. I know you understand this, right? 1 plus R versus 1 minus R.
Mm-hmm.
So
I think it's just being able to read it and plug it in
right.
correctly.
So this is what you have now. This is what you get later on down the road.
Mm-hmm.
And the hardest part, in my opinion, is this number here.
Mm-hmm.
Is figuring out how often.
Is that generally the years?
What is?
Is it the years?
So yeah, it could be years, it could be minutes. So in the problem, if it says
so you can always assume that the exponent is going to represent time.
yes,
Okay.
yes, but it may not be the number that you see in the problem, right? So
yeah. Okay.
Because if the half-life is every 10 minutes and you're running it for 20 minutes,
okay,
then how many half-lives do you have?
Sorry, what was the original?
If the half-life is 10 minutes,
yeah,
right, and they want to know like how much you have after 20 minutes,
then it's 2.
Then it's 2. It's
Mm-hmm.
power of 2.
Mm-hmm.
That's it.
Okay.